Hello again, everyone. I hope you can hear me fine. Because you're all muted, I can't hear you. If you are able to hear me, you can use the chat function to ask and send questions. So if you can be able to talk to Maria Popa, our education coordinator, she should be able to confirm to you if you are not getting the audio signal. If you have questions, I'll be able to see your questions. Please use the chat function to ask or send me questions. I may not be able to respond to your questions right away, but I'm promising to respond to all your questions at the end of the presentation. For those of you whose questions I'll not be able to get to, send me an email. I leave you my email and contact information at the end of the presentation. Then I can respond to all those questions. My name is Emmanuel Omondi. I am the research director for the Farming Systems Trial, which is the longest running side-by-side comparison of organic and conventional grain cropping systems. I am gonna be giving this presentation by making a brief history of the FST. I will share with you some of the results that we have seen from the FST over almost 40 years of existence, some of the lessons we've learned during that time period. Then I will talk about some specific practices that are useful that we have been practicing at Farming Systems Trial that are related with soil health or that go towards building the health of the soil. Like I said, the FST is the longest running side-by-side comparison of organic and conventional grain cropping systems, at least in America. The reason for starting it in 1981 was to help provide information to growers that intend to transition from conventional to organic, but also the FST provides information from the data we've been collecting to growers that have already transitioned. Some of those lessons that we've learned over the years would be useful to both growers that plan to transition and growers that have already transitioned. We are looking at three main cropping systems that we are comparing. We have two organic systems and a conventional. We have an organic manure systems, which is designed to produce grains for livestock. It's identical to a dairy or beef operation. It involves long rotations of grain crops as well as forage crops such as alfalfa or hay. Because it represents a dairy or beef operation, it has manure which we compost and use to supplement the fertilizer in the system. We have an organic legume systems which relies entirely on leguminous cover crops and cash crops in the rotations for providing the fertility of that system. Then we have the conventional systems, which represents the majority of grain growers in the US. It utilizes synthetic nitrogen fertilizers and herbicides for weed control. Beginning in 2008, we introduced no-till because reduced tillage in any system is good for building the health of the soil. The conventional system utilizes herbicides to control weeds in that system. The organic systems utilizes the roller crimper. I'm gonna have a few video clips. For those of you who have not seen the roller crimper in operation, you'll be able to see that today. We also introduced genetically modified crops, mostly just corn, genetically modified corn and soybeans, which are the main crops that we are testing at the FST. The areas of research, some of the data that we are collecting, we are looking at the yields, we are looking at the soil health, we are looking at the water quality and quantity. Recently, we've started looking at nutrient density differences between the systems. We are also looking at energy and economics. Some of the results we have seen for over time since 1986 up to now are shown in that chart. There was an initial decline at the farming systems trial when we started. This is normal for most systems. When you're transitioning from one system to another, there's usually a lag time when the soil organic matter is building up. A system that has been managed using conventional systems tend to decline in soil biology, and it is that soil biology that it needs to build soil organic matter to be able to begin supplying crops with nutrients. During that time period, when soil organic matter buildup is going on, yields can decline. So for the first 5 years of FST establishment, there was that decline. But since 1986, pretty much up to now, we have not seen statistical differences between organic and conventional grains. Conventional tend to produce a little bit more than organic, but statistically speaking, it's a tie. I combined the grains that we grow at FST, that's the wheat, corn, oats, and soybean, took the averages for me to be able to show you what's going on there in terms of yields, revenues, and profits. You see that the brown bar, which represents the organic manure systems, and the gray bar, which represents the conventional systems, the difference is not statistical. The green bar, which represents the organic legume systems, tend to perform a little bit lower than the other two, mostly because it is the lowest input systems. But if you factor in the revenues and the premium organic prices, you see that both of the two organic systems are providing profits that are 3 times to 6 times greater than the conventional ones. Now, those are results that are also being reported by other long-term studies across the country, which includes UC Davis, Iowa State University, University of Minnesota, University of Wisconsin, and another long-term studies in Maryland, that is managed by USDA ARS. The USDA has also conducted a census looking at just generally growers across the country that are practicing organic and conventional, and they are seeing the same results as those ones that we are reporting, that the conventional profits tend to be lower than the organic profits across the board. In fact, the conventional wheat from this census that was done by USDA, the conventional wheat and soybeans were actually losing money. Now that's something that we need, that a paradigm shift is required there. A lot of times when you talk to conventional growers and you ask them what the productivity of their farms are, they will equate productivity of their farms with the yields. So a yield-based productivity is probably not what they want to be doing. They want to look at the bottom line. Hopefully, when more growers are going to see the usefulness of having profits rather than just the yields, then we will begin to move, in my opinion, we'll begin to move in the right direction. Because most conventional growers have got access to credit, which a lot of organic growers don't. And they also have crop insurance, which most organic growers don't. So there's the tendency for conventional growers to not really pay attention to the bottom line. That's a paradigm shift required. What we have seen from the FST also is that organic tend to work especially well during drought years. In the period between 1988 and 1999, there were 5 years there when the precipitation was quite low compared to the other, 13 inches of rainfall compared to the normal 43 that we get in this region. During that period, especially 1995, the corn yields were 31% greater in organic system compared to the conventional. Soybean yields were double those of the conventional. Now, most organic growers tend to grow their corn later than conventional growers. The reason for that is just practical. The conventional seed normally is coated with pesticides. Towards the end of spring, there is normally an upsurge of pests in the soil. If your seed is coated with pesticides, then you can be able to grow your seed a lot earlier than those whose seeds are not coated with pesticides. In that picture that I hope you're able to see on your screens, the organic corn that you're seeing there was actually grown 3 weeks later than the conventional. But from the pictures you can see, the organic looks like it was grown 3 weeks earlier. This just goes to show what happens when there is a drought year, because 1995 was a drought year. And the organic does very well during such circumstances. These results have actually been published in peer-reviewed journal. I joined the Institute in 2015. Both 2015 and 2016 were dry years, not drought years, but the precipitation was significantly lower than other years. Again, those two photos were taken in September. We had a lot of rainfall at the beginning of the season, at the end of spring when we grow corn, and then it got really dry as the season progressed. This photo again was taken in September, and you can see the photo on the left, organic corn was looking a little bit happier than the conventional one. A close-up of those conventional corn suggested that they may have been also suffering from not just water deficiency, but it also looked like nitrogen and phosphorus deficiency symptoms. The purple color usually is a phosphorus deficiency symptom. The yellow color is usually a nitrogen deficiency symptom. It looked like the nitrogen and phosphorus fertilizers that were applied in spring when there was a lot of rain may have been lost in runoff erosion, such that it was not available at the time when we took these photos. In 2016, probably we are attributing this to the dry period of 2015 and 2016. We broke the record. For the first time, we got 200 bushels per acre in organic corn. Those were pretty exciting results, but I wasn't ready to express my excitement yet. The reason for that is because I had not seen the county averages, which we later saw, and it came to approximately 144 bushels per acre, which is within the yields that we obtained from the conventional plots. So then I really got excited about those results that prove again that organic systems work when there is periods of scarcity or when there is a drought. Now, the reason why organic does especially well during periods of drought, we attribute that to the health of the soil. That's something that we have been monitoring very closely between 1981 and now. And what we have seen over the years is that the two organic systems, the soil organic matter, has increased from about 3% in 1981 to approximately 4.3% in the two organic systems. Okay, there are some years when the soil organic matter has declined slightly, but the trajectory has been on an upward trend throughout the period. The conventional systems, on the other hand, the soil organic matter hasn't changed much. It has shifted between 3.2 and 3.5 and back to 3.2. This year it is at approximately 3.7. So that means we have more soil carbon and soil organic matter in the organic systems. Studies have shown that the more soil organic matter that you have, the more the ability of that soil not just to be resilient against the changing climate, but also to be able to provide more water to your crops. Rather than having more soil organic matter, we also find that the soil aggregates in the organic systems are better. Having greater amounts of soil organic matter means those microbes produce a gluing compound that we call glomalin, which binds soil particles together into aggregates. The more aggregates you have and the bigger those aggregates are, the greater the pores in the soil and the ability of that soil to filter water, in other words, to allow more water to percolate through. If you drop a clod of soil that has better aggregates, it tends to stay stable. If you drop a clod of soil that doesn't have as more stable aggregates, they tend to disintegrate. So this is what we see with soil that came from organic plots compared to soil that came from conventional plots. We have 72 plots at FST, Farming Systems Trial. If you remember what I said at the beginning, we had 3 initial systems that we are comparing until 2008. That is 2 organic systems and a conventional one. But from 2008, we now have 6 because those 3 systems are split between tilled and no-till. They are replicated 4 times each. Now, our ability to introduce a no-till in the systems was made possible by the wisdom of the individuals that started FST 1981 to have 8 replicates in each of those 3 systems. That was very good. In research, you just need 3 replicates minimum. Most field studies recommend having four replicates of every treatment that you are testing. 8 was an overkill, but 8 was good for us because when we introduced a no-till in 2008, we just split the tilled, the replicates between tillage and no-till system so that we had 4 replicates right there for the new system that we're introducing, tilled, and then the no-till and the till remained with also 4 replicates. So 6 systems times 6 of the systems that we are having, and then in every systems you have 3 points of entry. 3 points of entry are like subplots within each system. The reason for that is we have got different rotations in organic and conventional. So by having 3 additional subplots that we are calling entry points gives us the opportunity to be able to have multiple crops in every systems, which enable us to be able to analyze at least one of them using statistics. That means we have a total of 72 plots at the FST. Usually, you would need a map to be able to tell which plots are conventional and which ones are not. When we have small grains such as wheat, you would normally not require to have that map after a heavy downpour, because you will see a lot of ponding or standing water in the conventional plots. You don't see that in the organic plots just because of the glomalin soil aggregate situation that I just described. We have teamed up with Ohio State University recently to try and look at how those systems are affecting soil carbon stock or carbon sequestration. How are we sequestering carbon, and at what depths are we sequestering that carbon? A lot of studies have done carbon sequestration, but very few studies have looked at how the carbon is stored deeper down the soil profile. So these include taking deep cores up to 100 centimeters or a meter deep, and to be able to go that deep into the soil to get an intact soil core is difficult. This is why we use these hydraulic systems that we call the Giddings probe, that requires the power of the tractor to push that probe within which there's a tube that will collect the intact soil core for us, that is shown on the left picture. We then bring that soil to the lab and cut it at 0 to 10, 10 to 20, 20 to 30, 30 to 60, and 60 to 100 centimeters, and then analyze those depths separately to see how much soil is being sequestered in each depth and what are the chemical and physical properties that that we are getting from those depths. One of the things that you see immediately, as you can see in the middle picture over here, is that the organic soil tend to have deeper A horizon, or the darker part of the soil, the topsoil, compared to the conventional system. Again, that's just another indication of better soil health in the organic systems. The results that we have obtained, the preliminary results that we have obtained from Ohio State University, indicate what we have known before, but that provides evidence that organic systems actually are sequestering carbon, especially at the 10 to 20 centimeters and 20 to 30 centimeter depth, as well as 0 to 10 centimeter depth, even though the 0 to 10 centimeter depth, the difference is not as pronounced as in the 10 to 20 centimeter depth. They are dark brown. For those of you who can see this clearly, the dark brown bar indicate organic no-till. The light brown or reddish color is organic tilled, and then the light gray conventional no-till. The dark gray is conventional the other way around. The light gray is conventional till, and the last one is conventional no-till. You see that there seems to be a difference in the conventional between the tilled and no-till. The reason for that we attribute to the cover crop that is used by conventional. The conventional growers are now using some cover crops. There's fewer residues that are used by conventional growers. Even the conventional growers that are using cover crops take them out with herbicide so early. That's why at the end of the day, you don't see as much difference. You do see quite a bit of difference in the between tilled and no-till in the conventional systems. Whereas in the organic systems, where we have a lot of cover crops going on there, you don't tend to see much difference in carbon stocks between no-tilled and tilled system. We are also collaborating with a student at PhD students at the University of Tennessee, who is advised by Dr. Sindhu, who is a professor there. He is looking at labile and stable carbon analysis as part of his PhD program. For him, he is interested in just looking at the soil between 0 to 20, 10 to 20, and 20 to 30 centimeters here. The picture there on the left is me collecting the samples for him. We collected these samples for him and mailed them off to him. As you can see from that picture right on the extreme right, it does help to be able to balance on some of those probes. What we have seen also preliminarily from the University of Tennessee is the same results or the same trend that we saw with carbon stocks from the Ohio State University, that organic systems are storing, in the left, the right picture, are storing microbial carbon, which is the carbon that is stored within the microbes in the soil. Those microbial carbon, microbial biomass carbon is stored, there's a lot more of those in the 10 to 20, 20 to 30 centimeter depth compared to the 0 to 10 centimeter depth. What we are also seeing from James is that the gravimetric water content is there. It has a direct correlation, it seems, with the microbial biomass carbon, in that on the 0 to 10 centimeter depth, there doesn't seem to be much difference in the gravimetric water content, but in the 10 to 20 centimeters and 20 to 30 centimeters, we see the same differences as we are seeing with regard to microbial biomass carbon. These are all indicators of soil health and that we are doing something right, and we have been doing it for a long time. The reason why we are seeing this improvement in soil health is one of the biggest reason anyway, is because of diverse and long crop rotations that we have at the FST that also include diversity of cover crops. As you know, soil biology or soil microorganisms, they require a diverse diet, just like human beings require a balanced diet. Even the soil microbes require diverse diet, and the more diversity you provide them, the better they are going to perform. Reduced tillage also help to increase the carbon storage, as well as generally improve the soil health. So we are trying to look for different ways in which we can reduce tillage as much as possible at the farming systems trial. I mentioned crop rotations. Crop rotations is a very important part of the organic systems. Unlike the conventional systems that relies on chemicals, crop rotation is indispensable in organic systems. Our director, Mr. Jeff Moyer, usually says that there are many things you cannot control in your farm, but crop rotation should be one of them. That's one place that you can make a difference. You have to plan these things way in advance, and then you have to build in flexibility into your crop rotation planning, because the more flexibility you build into it, the better you're able to respond to changing conditions. Maybe 5 years down the line, you want to grow something different that is more profitable. 5 years down the line, maybe the climate changes that requires you to change your crop rotation somehow. So you want to build in the flexibility for you to be able to make those changes. This is a busy chart. I don't want you to focus more on what is there, other than this is just to show that how long we take to plan our crop rotation. The first chart actually that has got three rows, that is the manure system. And the second one is the legume systems with 3 rows. Again, the 3 rows represents what I mentioned as the points of entry, which gives us the flexibility of having multiple crops within each system. As you can see, between those 3 main systems of organic manure, like organic legume and conventional, the 2 organic systems have got more crops compared to the conventional system. I mentioned about the need to reduce tillage. Tillage is one thing that is indispensable in organic systems because it's one of the only effective way of controlling weeds. We are learning more and more how to control weeds with minimum tillage or no tillage at all, but we are not there yet. So a certain amount of tillage is required to be able to do that. The main reason why we till is to give the main crop advantage and also to keep weeds on the defensive. Now, weeds do not always have to be your enemy. If weeds are not going to affect your crops economically, then there really isn't any reason why we should take those weeds out, because they'll also be contributing towards improving your soil carbon. So we do need to establish the minimum weed density level below which it's not necessary to control them, but above which you may need to come in with intervention strategies. Tillage enables us to kill weeds, as I mentioned, and produce a clean seedbed that you can then be able to grow your crops in. Even after doing that, you're still going to end up with weeds, because weeds are very resilient and they will still be able to occur in spite of your best efforts. What we have found is that the best time to take out most of those weeds and to have the greatest impact sometimes is to take out weeds before you can see them. That's what we call blind cultivation. You can see the weeds, the roots is looking white. That's why we call it white root stage. At that point, usually 3 to 5 days after planting your cash crops, you are not able to see those weeds. You come in with a tine weeder and take those weeds out. The tine weeder goes down into the soil just about half an inch. We normally grow our cash crops a little bit deeper than that. So the tine weeds will not really get to your cash crop, but it will take away most of those weeds that you're not able to see. Sometimes we use rototillers, which is the picture right on the right, to also do the same thing, blind cultivation. A lot of times growers then come in with several secondary tillage operations, both to take out more weeds that came later and also to heal the soil on the rows, to be able to bury some of those weeds that are stubborn and within the row of the cash crop, in an effort to continue controlling weeds and end up with a clean crop at the end of the day that's not as affected by weeds. The problem is that the more tillage operations you're having on the systems, the more you're damaging the structure of the soil, and you end up with a situation such as what we are seeing in that picture. During a heavy downpour, a lot of that soil is going to get taken away by runoff erosion. It gets even worse than that. I have no idea how that guy got himself in that mess, but you can be assured that a lot of tillage on that soil had something to do with making that soil structure so weak that getting heavy equipment into that kind of soil, you might end up sinking. So for those reasons, we are looking for strategies to reduce tillage. And I would like to talk about that for the next few slides. As I mentioned earlier on, in organic systems, it's difficult to have a continuous no-till, such as the conventional growers manage to have continuous no-till. It's challenging. The conventional growers have the luxury of having herbicides. We don't, but there are options that we can use for reducing tillage, even in rotational, even in the organic systems. Some of the things we have tried, crop rotation is really important. With you rotating annual crops with perennial crops, if you can be able to include a perennial crop of, say, hay, alfalfa, and orchard grass, that would, the 3 to 4 years when you're having hay in there, is the 3 to 4 years that you don't have to till, and that reduces tillage substantially. Decreasing the amount of inversion tillage that is required is also another strategy for reducing tillage in organic systems. Instead of using moldboard plowing, use chisel plow or disc plowing that are less aggressive than moldboard plowing. Using the roller crimper, whereby the cash crops are no-tilled planted into a cover crop that has been terminated by the roller crimper, is one of the most effective ways that we have found for reducing the maximum amount of tillage in the organic systems. And I'm going to be talking about that quite a bit. The no-till roller crimping, even though we call it no-till, the actual name for it should be rotational no-till, because a certain amount of tillage is still required in that systems, especially when we are establishing those cover crops. It's really a two-step systems. You just draw, plant, and relax and wait to harvest. Usually, we get an average of 160 bushels per acre in the no-till systems, about 143 bushels per acre in the till systems. Now, the till systems include plowing, disking, packing, planting, several passes of rotary hoeing, cultivations, which can be several passes of those as well, and then harvest. Those are too many steps involved for getting the same amount of yield. So I think if we can be able to perfect or promote the use of reduced tillage, where you are just doing two things, roll, plant, and then wait to harvest and relax the rest of the season, do other things during the season, that is the direction that I think we should go to. In rotational no-till, in organic systems, we have two primary cover crops that we use. Hairy vetch is very popular with corn. The reason why we are using hairy vetch, matching it with corn, is because it fixes nitrogen. So it not only provides control of weeds, because after you roll it, it controls weeds for you, but also provides nitrogen to that corn. As you know, corn requires a lot of nitrogen compared to beans. This is what you want to see if you planted your cover crop at the right time, and I'm going to be talking about why it needs to be planted at the right time, why it needs to be terminated at the right time as well. If you planted it at the right time, you end up with significant amount of biomass in that hairy veg. This is what you end up seeing. Weeds control effectively. Even 5 weeks later, you hardly see any weed in that corn crop. With regard to soybean, we prefer to use cereal rye, mainly because cereal rye does not fix nitrogen, but soybean does. So it requires a crop that is going to produce quite a bit of biomass to control weeds. The thing is, soybean does not canopy as quickly as corn. So you do need a little bit more biomass than you need for corn, because corn would canopy and then would provide a living mulch that can control weeds for the rest of the season. Soybean will take a little bit longer. So the greater the biomass of the cover crop you use, the more effective is your weed control going to be. I'm going to run a video here to just show you what is involved. It's just a 1-minute video for those who have not seen this happening before. So we are rolling the cover crop. That's cereal rye mixed with the Austrian winter wheat, and planting beans into that cover crop all in one pass. It's important to stop every other row to check to make sure that your seed is actually getting into the soil. If the seed doesn't get in the soil, like the soybean seed that we can see there, it will not germinate. There has to be a soil to seed to soil contact for you for these beans to germinate and become a crop that you can harvest. If you are seeing a lot of your seeds remaining on the surface, maybe because the biomass is too heavy, sometimes strategies such as the shark tooth residue managers, some people call it raw cleaners, would be able to take away some of those residues and enable the seed to have a better opportunity at getting to the soil. The residue manager is located here where it says shark tooth residue manager, if you can see this photo. The no-till planter is specially designed also to have additional weight so that the whole planter can be able to get better into, to penetrate better into the thick cover crop mulch. The residue manager has to be adjusted. If it is misadjusted or if it is too deeply adjusted, it creates more spaces that could potentially result in having weeds. So you need to play with it, raise it or lower it until you get most of those rows, the cash crop rows, covered effectively so that you're not inadvertently ending up with too much weeds. This is what you want to see if you planted your cover crop at the right time in the fall, you terminated it at the right time in spring, then you would be able to see this. In organic systems, especially systems that rely on cover crops, timing is everything. You need to successfully terminate the cover crop. You need to have adequate biomass for weed control. Rye is usually planted, drilled in between late August and early November, a bigger window than vetch, which is usually planted between mid-August and late September. Then the cash crop needs to be planted or roller creamed in the mid-May to early June at the anthesis stage or when it's beginning to produce pollen. You miss those windows, you'll end up with a situation such as the one we see here. And that is possible with organic systems. Sometimes climate dictates when you're going to put those cover crops out. Sometimes climate also dictates when you're going to terminate it. So timing is everything. We have to try our best to keep ourselves within those timings for us to be able to get results, better results. As you can see from this study that was carried out between Rodale Institute and Penn State University, we were able to show that the earlier you're able to get this cereal rye in, the better you're able to, the more the biomass concentration that you end up with. Those that were planted in early to late October ends up with a lot less biomass concentration than those that were planted between 26th of August and 15th of September. The time when the cover crop is terminated also matters. As you can see, the dotted line represents a termination date of May 20, the continuous line a termination day of May 30. Just 10-day difference makes a big difference in the amount of biomass content that you end up with at the time when you're terminating the cover crop. So the earlier you can plant your cover crop and the later you can manage to terminate it, the better the results. So what do you do when this happens? When this happens, that's not the end of the world. You can still be able to rescue this situation by using the high residue cultivator, which is specially designed to be able to take weeds in 30-inch row spaced crops. It has a residue slicer that slices through the cover crop to allow these sweeps to ride underneath and take out the weeds. The residue slicer is located between two press wheels because that would press down firmly onto the cover crop mulch so that you're not spreading it out and making a mess of the mulch. You still want that mulch to continue controlling the weeds for you. So by having this situation where you have the residue slicer doing a clean cut or a clean slicing of the residues, prevents the possibility of ending up with the mulch spreading all over the place. And it works just as well with the beans, soybeans, as with corn. I'm going to play another video to you just to wrap it all up, so from the time when we are rolling these cover crops to situations that require the use of the high residue cultivator.
Rodale Institute utilizes the innovative roller crimper
Sorry about that. I'm raising the volume here. Okay.
As the primary weed control tool in an organic rotational no-till corn and soybean production. This method involves simultaneously rolling a dense cover and planting a cash crop into the mulch layer using a modified no-till planter. The chevron shape of the crimper blades ensures that the stems of the cover crop are broken in so many places that they cannot recover and will create an evenly distributed mulch layer. In normal years, the thick mulch suppresses weeds season long. However, unexpected weather conditions such as high precipitation at the time of rolling crimping, late planting of the cover crop in the fall, or rolling the cover crop before the effective termination growth stage, which is normally at flowering or anthesis, can result in substantial weed infestation. An innovative tractor-mounted implement called a high residue cultivator is utilized as a rescue response to manage weeds in a rotational no-till system. The high residue cultivator has residue slicers that cut through the cover crop residue mulch to create a path for the sweeps to ride under the mulch just below the soil surface to cut weed tops from their roots or uproot them. Two press wheels on either side of the residue slicers press down firmly on mulch residues, thereby facilitating clean slicing of the residues, ensuring that sweeps riding under the mulch leaves the mulch intact and relatively undisturbed. This is important in ensuring that weed suppression from the mulch is not impaired.
Just a few more slides. I have been talking about FST, but I also wanted to show that rotational no-till is not just defined or confined to grains. It works just as well in vegetables. We are accustomed to seeing this situation where we can use a dry straw to help control weeds as well as to conserve some moisture in between the rows of vegetables. We can also use the same roller crimper to roll down the cover crop and plant vegetables into the rolled down cover crop using a modified or a no-till transplanter. On the left picture here is my colleague, Dr. Gladys Inati, getting ready to transplant some of her research plots. This video here, which is just about 30 seconds, shows Dr. Gladys Inati doing exactly that, planting squash into that rolled down cereal rye. And this is what you see 6 weeks after no-till transplanting the squash. If you had a thick enough cereal rye, you should be able to control most of the weeds season long. In California, this picture was taken in California. Again, those are large farms that involved no-till transplanting eggplants in rolled down cover crops, just exactly the same way as Dr. Zinati demonstrated over in the video I just showed. The roller crimper is what we'd call scale neutral. You can see the one on the left over there. That's one that is specifically designed for raised beds, which is how most vegetables are grown. For those with smaller, maybe backyard gardens and want to utilize the roller crimper, they are available. You can attach them to a walk-behind tractor, and that would be able to cover much smaller spaces that most vegetables are grown in. There's a lot more that is involved in this process of no-till, reducing tillage in organic systems, but that's all I'm able to cover today. And now I would welcome questions. I don't know if there's any question that has been posed yet. I'm not seeing any question right now. If you have any questions, this would be a good time to ask them. If you don't have a question right away, those are my contact information. You can reach me through email, eomondi@rodelinst.org, or through phone, 610-683-0555. 1459, and I'll be able to respond to your questions. There is one question here. What's the next? What is the question from Beth? She wants to know what's the next direction for our study. That's a good question. We are looking at different things. Like I said, we have not perfected the art of making sure that the rolling crimping takes away all the weeds all the time. If we can be able to come up with cover crop combinations that can help us to do that, then that's the direction that we want to do. So we are looking at various cover crop combinations. We are looking at the possibility of using plant breeding strategies that can be able to give us cover crops that are more effective in controlling weeds. We are looking at coming up with crops that are more tolerant to weeds, so that the threshold when those weeds need to be taken out is a little bit higher, so those crops can be able to survive with weeds. We are looking at the potential of using hemp as both a cash crop, industrial hemp, as both a cash crop and cover crop. We started doing that last year. That was the first time that hemp has got a license, the first time that hemp has been permitted in Pennsylvania. So we are looking at the potential of using hemp also as both a cash crop and cover crop to see whether that would be an effective way of controlling weeds. I have a second question here from Pam. She's asking, on the no-till corn, what fertilizers were applied, or did the veg provide all the needed nitrogen? That's an excellent question. We typically don't apply fertilizers to the no-till organic corn. If you're asking about no-till organic corn, we typically don't apply any fertilizers. We do apply composted manure though. Every 3 to 5 years, we do apply composted manure to supplement the nitrogen fertilizers that is being provided by the veg, the nitrogen that is being fixed by veg. Now, the application of composted manure is only done in the organic manure no-till system and organic manure till systems. The organic legume systems, we don't apply any fertilizer. It only relies, as I mentioned earlier, entirely on the nitrogen fixation by leguminous cover crop and cash crop in rotation, such as soybeans. I think those are the only 2 questions I have been able to get today. If you have additional questions, again, please get in touch with me directly by either through the phone or the email, and I will be happy to respond to your questions. I want to thank you very much for coming to this webinar, and I want to apologize that we had technical difficulties that resulted in this session starting later than we had planned. But again, thanks very much and hope to hear from you soon.